Okay, today what we're going to do is we're going to look at a kind of a development of the proof for the chain rule to figure out what happens when we want to take the derivative of a composition where we have f of g of x and we want to take the derivative of that with respect to x. And so the idea here is that we have to realize that composition itself is going to play a role in how fast the rates of change are changing. Now, what we're going to do first is we're going to start with some examples. I will say that we're not going to do the formal proof for this because it is very long and kind of outside the scope of what you're going to need to know for AB calculus. But what I do want to do is kind of help you kind of see how it works and why it works the way that it does. So first we're going to take a look at an example, a simple example. We're going to define our function f of x is going to be just a nice linear function, negative 1/3 x plus 2. And then clearly our derivative of that function is going to be negative 1/3 because I picked a linear function because it has a constant slope, which means its derivative, its rate of change is going to be constant. Then we're going to take a look at g of x, and again I'm going to pick a linear function, something fairly simple. G of x equals 2x, and so g prime of x is of course going to be 2. So those are two kind of simple ideas. We have these linear functions that we're looking at. Now what I want to do is take a look at what do I actually have if I were to take the composition of these functions. And remember, with composition, we're basically plugging g of x into f of x. So we would take our rule for f of x, and instead of the x, I'll just put the parentheses in here because that acts as a placeholder, and we're going to plug in our 2x there and then simplify. So we would get negative 2/3 x plus 2. So if I was going to try to take the derivative of f of g of x with respect to x, then if I am trying to take this derivative, notice that I can come over here to the rule that we just found, that the derivative is simply going to be the slope. It's going to be negative 2/3. But what I want you to see is that the negative 2/3, notice that I multiplied the rates of change for the inside function and the outside function. That if I take the inside function, which is 2x, its rate of change was 2, the outside function's rate of change was negative 1/3, and the resulting rate of change of the composition was negative 2/3. And it is not coincidental that the slope of the composition is exactly equal to the slope of the outside function, slope of f of x, times the slope of the inside function, g of x. Or in other words, we can think about it that we're basically taking the rate of change of f of x at an x value times the rate of change of g of x at an x value. Now I added in the at an x value because I picked a very simple example because at any x value f of x and g of x had constant rates of change. But it doesn't really matter if you are talking about it with functions that have changing rates of change, where you have not a constant rate of change. Like for example, x squared does not have a constant rate of change. It depends on where you are on the curve. That this idea that you're taking the rate of change on the inside function times the rate of change of the outside function. Right? Now another way to look at this is in kind of the idea of transformations. So suppose we have a function, okay, such as y equals f of x, and that what we're going to do is we're going to transform this function by taking a look at f of 2x. Okay, so this is going to be where we're kind of doing a composition where our inside function g of x is the 2x, and the outside function, so I am doing f of g of x, a very simple composition, which is my f of 2x. Right? And we want to see, well, what does that do to the graph? Well, what I want to do first is I want to take a look at this graphically. So I'm going to pull up the calculator, and it doesn't really matter what the function is, so I'm just going to graph it and then show you kind of the results of f of x and f of 2x, and I want you to think in your head what transformation is happening here. Alright, so here's our example. Like I said, it doesn't really matter what f of x is. Here's my f of x function coming here in blue. And here's my f of 2x. That what we want to remember is that f of 2x really causes the graph to have a horizontal shrink by that factor of 2. That the idea is that we basically are moving every point on f of x. Every point that we have here, we're moving it so that its distance from the y-axis is half the distance that it used to be, so that it now ends up right here. And if you compare your distances, here is the original distance from the x-axis, here's our new distance, and that new distance is half the distance. And the question that we want to ask ourselves is, what happens to the slopes? What do we notice while the x values moved half the distance closer? That what happened to the slopes? The slope at this point, this corresponding point right here, actually ends up having a steeper slope, right? So by smooshing it in this way, what we've done is we've scaled the slope so that we have steeper slopes. So the slopes on f of 2x are steeper than what they were on f of x. Okay. And another way to think about this, and let's go back to the example that I just did previously, that basically what we saw previously is that we ended up taking the rate of change of the inside function times the rate of change of the outside function. And if I were to kind of think about the tangent lines and draw the tangent lines and compare the slope right here compared to the slope right here, and you might be, well, what's the factor that it's going to change? And if you take a look at it and you're like looking at this, you can see that if I get steeper, by how much did I get steeper? I got twice as steep. I'm going to go up twice as much to get to the same idea. That it actually is this kind of idea, the rate of change on the inside function multiplies times the rate of change on the outside function to give us what the slope is going to be. Now, another way to think of this in kind of layman's terms is that when you're looking at this idea of this x-axis, that the x-axis on f of x, think of it like a treadmill, and it's a treadmill that's not moving. So the rate of change that you see on f of x is purely based on the function f's rate of change, how fast it's changing in any given instant. But then if we take our x-axis, and when we introduce this 2x change in here, what we're doing is we're turning the treadmill on. The 2x is going to cause us to move through the x values twice as fast as we were originally over here. We will get to 1 sooner than we would have gotten to 2. Right? And so the idea is, because I'm speeding up the x-axis, the speed that the inside function is changing is also going to change how fast I get to the point over here. And so the new rate of change is a combination of the speed that I'm moving through the x's and the speed that f had originally. And that's where that product of rates of change is going to come in. All right, another way to think about it, and so let's go ahead and write the rule down so you can see kind of where the notation is, and we'll kind of show a couple different perspectives on it. So the rule for the derivative of a composition f of g of x with respect to x, what you're going to do first, okay, is, well, there's kind of two perspectives on it. I'd like to figure out, well, how fast is f moving at the corresponding x value? So we're going to figure out the derivative, but with the g of x in there. Right? So it's kind of like we're going to ignore the inside function and figure out how fast the outside function is going. And then once we figure out how fast the outside function is going, then we're going to multiply that times how fast the inside function is going. So it's kind of like the treadmill problem. We're going to take how fast we went through the x-axis times how fast f was in originally. So you basically have two things that are contributing to your rate of change that you have to take a look at. Now let's look at this another way. Okay, we're going to kind of use Leibniz's notation with our dy dx notation. So if I have y equals f of g of x, then basically what I'm trying to do is I'm trying to find dy dx. What I'm going to do here is I'm going to introduce kind of a u substitution. So I'm going to let u equal g of x. And so the idea is that what we're going to do is we're going to transform our function into y equals f of u. Now, because my variable is f of u, when I take this derivative, since I'm going to take it with respect to u first, I'm really finding dy du. That would be the f prime of u that we have there. But notice what I'm trying to find is not f prime of u, I'm trying to find dy dx. So the problem is that I'm taking it with respect to u. Well, the trick to this is to recognize that when I have this function, well, du with respect to x is something that I can easily calculate because u is a function of x. This one you can just calculate by doing g prime of x. And if you think about what we're looking for and what these two parts have given me, that if I want to find dy dx using our infinitesimals, if I were to take the derivative of y with respect to u and then multiply that times the derivative of u with respect to x, so I'm basically taking the two components that I found, my g prime of x, the speed that the inside function is changing, and then dy du is the speed that the outside function is changing. And notice that in our little symbol, this should make obvious algebraic sense to us because we can kind of think of that as canceling out the du's, and then we end up with dy dx. So, and then saying, well, what is it that I exactly found? Remember that dy with respect to u was f prime of u times du dx was g prime of x. And then because whenever we do a u substitution or a transformation, we have to go back to our original variable. This is f prime of g of x times g prime of x. And so we're basically getting the same rule by looking at it through Leibniz's notation. The derivative of the outside function times the derivative of the inside function. Okay, so that's another way to look at it. A fourth way to look at this is to kind of look at it in terms of our limit definition. Now, using the limit definition to kind of explain this, I'm going to admit that we're not going to do the formal definition and do a proof like we did on some of the others, because it does tend to get a little very complicated and a lot of algebra and just more than what we really need to know. So we're going to kind of do what I call math pigeon language. We're going to kind of gloss over some of the finer details, but kind of get the essence of what would happen with the limit definition. All right. So let's go back to our simple example first, because I think that kind of makes sense, and we'll work our way to the more general one. So if I had f of x, I'm going to define that as a function, y equals f of x, and then I'm going to take a composition where I'm going to define it as f of 2x. And so my inside function is 2x, and that does have a constant slope, because I'm going to start with the easy ones where they have a constant slope that it is changing. So we know that because of this, we're moving through the x values twice as fast. So we would take our slope for f times 2 to get our resulting slope of the composition. But let's see what happens on the limit function. So if I want to take the derivative of f of 2x with respect to x, then basically we're going to try to do the limit as h goes to 0 of f of, and remember you plug x plus h into your function, and so it has that extra 2 there, so we're just going to plug it in, minus our f of our function, which is f of 2x, all over h. So that's kind of our initial start to this. Now we're just going to do a little algebra and simplify. So we have the limit as h goes to 0 of f of 2x plus 2h minus f of 2x all over h. Now, what I'm basically going to do here, because we're trying to get it in a nice form that we know how to do the derivative of. And the problem we have right now is that we have some 2x here and an h and a 2h, and so things aren't matching up here. So what I'm going to do is I'm going to let u equal 2x, right? So this is now going to turn into the limit as h goes to 0 of f of u plus 2h minus f of u all over h. So I do that first. Now the other thing that I don't like is the fact that this right here, this 2h, well, that's kind of bothering me, because in the limit definition, if we go back to the limit definition, it was u plus some small number h minus f of u all over h. That would be, we're really close to the limit definition of a derivative. And so if I could get something to kind of work out here, maybe I could end up with a limit definition and be able to kind of use the definition we already have from 3.1. Well, I'm going to utilize our trick, which is we can always multiply by a form of 1. Now I'm going to conveniently choose to multiply by 2 over 2, because 2 is what I'm missing from down here to get these two things to match. Okay, and you could also think of this 2 as the rate of change of the inside function. So I multiply by this form of 1, and I'm going to conveniently rearrange this to be f of u plus 2h minus f of u all over 2h, and now there's this extra 2 here. All right, and the limit of a constant times something, you can always do the constant times the limit. So I can actually pull this 2 out, okay, and put it in front because it's a constant. Now, the next thing that we want to think about here is I'm going to kind of let, and again, I'm using a little bit of pigeon math. I'm not being as formal as some other calculus would be, especially if you were in BC Calc. I'm going to let capital H equal 2h, just so I can kind of work my way toward getting it in the correct form. So we're going to come down here to the next line. So I still have the 2, still doing the limit. I'm going to fill something in here in a second, so hold that thought. F of u plus h minus f of u all over h. And so basically the idea here is that let's think about this limit and kind of why I left this blank. As little h goes to 0, what do we know about big H? Since it's 2 times h, if I was going to say, well, what's going on? As h goes to 0, doesn't capital H go to 0 as well? That these are going to the same place, they're going to 0. And since I'm doing this limit as little h goes to 0, I can actually change this to be the limit as big H goes to 0. The idea is you can kind of go change this to h equals little h equals h over 2. And then when I substitute that in, h over 2, multiply both sides by 2, you're still going to go to 0. You might not be going quite the same speed, but you'll get there eventually. So I can change this to h goes to 0. And again, I'm waving my hands a little bit. We're doing a little bit of bad math here, but it's kind of to get the idea. And what you notice then is this is nothing more than the derivative. This is f prime of u times 2. And then because we transformed and we put ourselves into the u, we want to go back to our original variable. That's really 2 times f prime of g, or sorry, in this case, my inside function was 2x. So what we have shown with this limit definition is that the derivative of f of 2x with respect to x ends up being 2 times f prime of 2x. Notice that, what is this? Where is this coming from? That is the rate of change of the inside function 2x. And again, I picked this really simple example because I wanted it to have a constant rate of change, so it makes it easy to see kind of what happened in the limit definition, right? And so this is exactly giving us, when I am looking at this problem, if I have f of g of x, this is g prime of x times f prime of g of x. Now, let's do one more limit definition. Let's be a little bit more general than what we were. So we're going to now do the derivative of f of g of x with respect to x, and we're going to use our limit definition. So that would be the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. So we do the same thing, we're just applying the limit definition. Now, the trick here is, because it was easy when I had a constant for my function g of x was x 2x. So it was pretty easy to go 2 times x plus h. Well, I'm keeping this general now. What we do want to think about is that basically doing this x plus h in the problem is basically going to give us a function that's a little bit different than g of x, but it's based on g of x. And so the idea is what we're going to say is that g of x plus h, it's kind of a little side comment over here, minus g of x. The difference between this new function and g of x, we're just going to give this a name. Okay, we don't really know what it is. We're just going to call it the change based on h. So I'm going to call it delta h. Right? And then if I do that, I can rearrange this and say g of x plus h is going to be the original g of x plus this change based on the fact that I did x plus h instead. Okay. So we're going to put that in, the limit as h goes to 0 of f of, so I'm taking out g of x plus h, and it's going to become g of x plus some change based on that composition minus f of g of x all over h. Okay. And so the idea that we have, same idea that I did earlier, I'm now basically going to do the u substitution. So what I'm going to do is I'm going to let my u equal g of x, just like I did on the previous example. So this is going to become the limit as h goes to 0 of f of u plus this change in h minus f of u all over h. Right? And here's where a little bit of the bad math comes in. That what I want is I need to multiply this by a form of 1, and that form of 1 needs to be based on kind of the derivative, right? And so when I go to multiply it based on that derivative, I can kind of think about it like I'm going to do, and you'll see why in a second why this is going to work, that if I multiply by this change in h over change in h, that multiplying by this form of 1 is okay, right? Because I'm multiplying by a form of 1. And if I multiply by this form of 1, then I'm going to rearrange it, the limit as h goes to 0, f of u plus delta h minus f of u. I'm going to put 1 delta h here, and then I'm going to move this one over here, so I'm going to have times delta h over h. Now, what I can't do, like I did in the first problem, is pull this out to the front because this is not a constant now. This depends on what g was, and so the change in h, we're just going to leave it right now over here, and then we're going to have to address it later. I can't pull it out of the limit. What I am going to do, however, is I'm going to split this. I'm going to make it the limit of a product is the product of the limits. So the limit is h goes to 0, f of u plus delta h minus f of u over delta h times the limit as h goes to 0 of delta h over h. Okay. So again, because this is not a constant, I can't pull it out like it was in the simple example. But now I'm going to remember that delta h, which I have written up here, delta h is g of x plus h minus g of x. That's how I defined it originally. So now I'm going to put that back in. All right, the limit as h goes to 0, f of u plus delta h minus f of u all over delta h times the limit as h goes to 0 of g of x plus h minus g of x all over h. And now hopefully some light bulbs are going off. What is this right over here? This is exactly g prime of x. So this is our definition of how fast the inside function is changing. There's my g prime of x. All right, now over here, using the same kind of strategy I did in the last one, I'm going to utilize the fact that as h goes to 0, my delta h is going to go to 0 as well. Because if you think about it, as h goes to 0, doesn't g of x approach, g of x plus h is going to end up being g of x? And so the difference between the two functions becomes smaller and smaller and smaller, and then when h gets to 0, it's the same function, it's going to go to 0 as well. So we can pretty much take out this and think of this as we are doing the limit as delta h goes to 0 of f of u plus delta h minus f of u over delta h. And that is exactly the definition of the derivative of f prime of u. And then times our g prime of x. And if we go back to our original variable, g of x is u, so f prime of g of x times g prime of x. So the idea here is that when we were looking at this, that we're basically going to do the derivative of the outside function, bringing along your inside function, times the derivative of your inside function. Now the idea is, and this chain rule, kind of the idea of how this works. So now we're going to go into the actual notes for this from the packet, that what we're doing here is, why is it called chain rule, is that it's kind of like a chain reaction, that you're going to start on the inside function and figure out the rate of change of the inside, work yourself out, find the rate of change of the outside function. And what if there were three compositions involved, three functions in our composition? We would get the rate of change of the innermost function, multiply that times the rate of change in the second function, and then multiply that times the rate of change in the third function. So we end up with this idea of the mousetrap game, where you start something off and then all these chain of events kind of follow along for each other, or pushing the domino, hitting one domino causes all the rest of them to fall. That this is the idea that we're looking at. And so kind of using Leibniz notation, what we're basically saying, and this is obviously a really long one, I'm trying to figure out the rate of change in some function p with respect to a. And so maybe I first have to figure out, starting on the inside, the rate of change in b with respect to a. But then I find the next outside function, the rate of change of c with respect to b, and then find d with respect to c, and keep following this along until I get to the end. And kind of what you see when you're looking at this chain reaction, where you've found all the rates of change of the inside functions, that you'll see you have a lot of nice cancellation. Leibniz notation is great because it mathematically makes sense to us that we're going to cancel out all of the kind of links in the chain, and that we would end up with dp over dA. And so we can always use chain rule to differentiate composite functions. Functions that have other than the trivial x within the other function. Now, the chain rule actually works for all functions, because if I think about like this as a composition of f of x equal to x squared minus 1 and g of x equal to x, what's the derivative of g of x? It's just 1. So it's unnecessary, and you don't need to think of it as a chain rule problem, because the derivative, the rate of change of your inside function, is 1. And so that doesn't affect anything. So without chain rule, anytime you see any of these, we could do this without chain rule. But as soon as you start to see something like this, what you have to recognize is that you have a composition of functions. And you have to have that skill of decomposing the functions into an inside function and an outside function. So our inside function, say for this first example, u would equal x squared minus 1. Our outside function would be y equals the square root of u. Our inside function here, u would be 5x. Our outside function would be sine of u. Our inside function here, u would equal 3x minus 2. Our outside function would be u to the 7th. Our inside function would be, now this one's kind of interesting. This is a difference of two functions. And remember, the derivative of a difference is the difference of the derivative. So the x is not what I'm even considering here. This is just going to be easy to take the derivative of. It's this part that is a composition. So I would let my u equal x squared. And the outside function I'm going to be looking at is the tangent of u. And if I wanted to take the derivative of this, I would basically take the derivative of the x and then worry about the tangent of x squared using chain rule. Okay? And so the idea is we want to determine the rate that the inside function is changing. So you're going to find du dx, and then you are going to multiply that times the rate the outside function is changing. So you're going to find dy du, and that of course is going to give us dy dx. And you do have to make sure at the end that you basically put back in your u, because we want to go back to the original problem that we had. That we're only doing this transformation to help us determine the rates of change. So here is our function y equals f of u, where u is the inside function. And our f is going to be the outside function. And that we know that if we want to find the derivative of that, we're going to take the derivative of the outside function with respect to u, and then take the derivative of the inside function with respect to x, and that when we multiply them and change all our variables back, we are going to get the derivative we're looking for the composition. And you do want to think about this like you're peeling an onion. You're going to go one layer at a time. You're going to you can either work from the inside out or the outside in. I kind of like to identify the inside function, find its rate, and then work my way to the outside function. So there's different ways that you're looking at it. And it's kind of called the chain rule because there are as many links as there are embedded functions. Because this would be link number 1, this would be link number 2, because you had 2 functions that you were composing. If I had 3 functions that I was composing, say for example, y equals f of g of h of x, that when you're doing this, you're going to let u equal h of x, and you're going to find du dx. That's going to be your first link in the chain. And then because you let u equal h of x, you're now f of g of u. And the problem is you still have a composition. So now I'll pick another letter. Usually they pick v. I'm going to let v equal g of u. And then I'm going to calculate dv du, because that's the variable that's in there. All right, and then this becomes, let me move that out of my way. This becomes f of v, all right, and then so now we're going to find our rate of change on f with respect to v. So we're going to find dy dv, because y equals this. And then we notice that, hey, if I were to multiply these together, put the links in the chain together, du dx times dv du cancels, dv dv cancels, and my final answer would be dy dx. That you basically find each link in the chain and work your way up through the function. Okay? And that's why we say there should be as many chain links as there are embedded functions. 3 functions in the composition. Notice I have 1, 2, 3 chains to put together. And this is why Leibniz's notation is really good for this, to really kind of see what you're doing. All right, so let's look at a couple of examples here just to see how this works before we end this video. So the way that I would work this, and you do need to kind of do some work on the side, I'm going to first figure out my inside function, x squared minus 1. I'm going to figure out du dx, which is 2x. See, it's pretty easy. Then once I do that, I'm now basically going to think of this as trying to find the derivative of the square root of u, or u to the 1/2, with respect to, maybe I want to change that, my notation. I kind of like to do all the work over on the side. So once I like to do the inside and the outside function. I think it makes it easier down here at the bottom. So I do the inside function, and then I find what the outside function is, and I go, well, the outside function, y equals u to the 1/2, and then I find dy du. I like this notation better. And dy du would be 1/2 u to the negative 1/2. See, nice, easy little derivatives. and then I put them together, okay? So I put my chains together, and I know that du dx times dy du is going to be 1/2 u to the negative 1/2 times 2x. But then you have to remember to put your u back in. So we do 1/2. Our u was x squared minus 1 to the negative 1/2 times 2x. And so the idea is you have to kind of do several parts of this as you go. Now, as we get better at this, and especially if it's only two functions put together, sometimes you don't need to write as many of the steps out in order to figure out what the actual chain rule is doing. Notice that if I can in my head just kind of go, hey, that's the inside, that's the stuff, and this is stuff to the 1/2 or u to the 1/2, the derivative of u to the 1/2 is 1/2 u to the negative 1/2. And then I just have to remember to take the derivative of the stuff inside. The derivative of u is 2x. So you can kind of pretty much, you can see what I'm doing over here, but you don't really need to show all of this work. As long as you can kind of in your head go, well, the inside function is this. Here's its rate of change. Here's your outside function. Here's what its rate of change is going to be. And then put it back together, you'll be fine. Now I'm going to do, let's do this one the short way, because this one's not too bad. So I would, kind of the work that I would show is I'd say u equals 5x and du dx equals 5. And then at this point in my head, I'm just going to go, hey, this is sine of u. What's the derivative of sine of u? Derivative of sine is cosine of u, put your u in there, times, and then you immediately follow it with times the rate of change of the inside function, which is 5. So our final answer would be 5 cosine of 5x. So usually the amount of work that I show, instead of showing all of this, I typically do the inside function and then just do the outside function in my head. Like for example here, in this next one, I would say u equals 3x minus 2, du dx would be 3. So if I want to take the derivative of this, I would think of this as u to the 7th. What's the derivative of u to the 7th? 7u to the 6th. And then because I'm saying u, I need to follow it with the inside rate function, and that would be 3 times 3. So my final answer would be 21 3x minus 2 to the 6th. And you can see the power of this just by looking at this problem. Before I had chain rule, I would have had to distribute and multiply this out, take 3x minus 2 times 3x minus 2, get the result times 3x minus 2, and do that 7 times, and then use the power rule to get the derivative, whereas here, all I have to do is take the derivative of the inside function and know that I'm taking the derivative of the outside function times the derivative of the inside function. And that's how we're going to do chain rule. All right, here's that example we had from the beginning. Now, and again, the first thing I'm going to notice, I'm not going to worry about chain rule until I have to. The derivative of a difference is the difference of the derivatives. Derivative of x is 1 minus, now I have to worry about chain rule, because I have the derivative of the tangent of x squared with respect to x. So there are times when you run through your derivatives, you can kind of show this notation to say, I need to take this, but it's hard, so I'll do it in the next step. My u is going to be x squared. My du dx is going to be 2x. So therefore, when I go to take the derivative of this, don't forget your 1 minus, the derivative of, now I'm going to ignore the inside and go, I need the derivative of the outside, tangent of u. The derivative of tangent is secant squared of u, which is x squared, times the rate that the inside is changing, which is the 2x. So my final answer, 1 minus 2x secant squared of x squared. All right? And so you can kind of see how this works. Now, here's an example. On this, we could be using quotient rule. I mean, it's perfectly fine to do quotient rule on that. But what I can do instead, now that I have a chain rule, is think of this as x plus 1 to the negative 1. And I want to take the derivative of that. So I'm going to use the inside function is x plus 1. The du dx is going to be 1. So now I come up here and say, what's the derivative of the outside? U to the negative 1 would be negative u to the negative 2. I forgot I was not writing the u's in there. So u happens to be x plus 1 to the negative 2 times the derivative of the inside, and notice I got my negative 1 over x plus 1 squared. Now I don't care if you use quotient rule here or if you use product rule here, or product rule or chain rule. Sorry, quotient rule or chain rule. Either one is going to be perfectly fine. All right, let's do one more down here. And now what you have to notice with this one is this is a 3-part chain. There will be 3 parts to our link. Let me rewrite this where I have it as its sine of 3x squared. So the idea is you got to figure out what's the innermost function. So I'm going to let u equal 3x. So that's going to give me du dx is 3. So I do that first. Okay. Now I'm going to come out and say, well, if I'm taking the derivative of this, then I would think of this as the derivative of sine of u squared. And then I realize, oh, wait a minute, I've got to keep going here. So now I need to figure out the derivative of this with respect to u now of sine of u squared. Okay, but now I'm like, wait a minute, that's still a composition. So now I do it again, except this time I'm going to pick, say, v. V, my inside function is sine of u. dv du is going to be derivative of sine is cosine. Okay? So now when I come up here, what I'm trying to do now is take the derivative with respect to v of v squared. So notice this time I'm actually putting the substitutions in because this one was 3. It's a little bit harder. What's the derivative of v squared? The derivative of v squared is going to be 2v. Now let's work our way back. V was sine of u. U was 3x. But now remember, you have to multiply it. You got to work your chain back. This is the derivative of this with respect to v. Now I need to do it dv with respect to u, so I have to multiply by, and I'm going to come, let's move this whole thing down here. I need more room. 2 sine of 3x times my dv du, cosine of u, times du dx, which is 3. So notice that kind of if I put underneath of it using Leibniz notation, this part here was my dy dv. This was my dv du, and then this one was my du dx here. So those are my 3 parts that I'm essentially looking at. I had 3 functions, 3 links in the chain, and each time that you go, and then at the end, remember, you just have to put back all your variables with x. So our final answer in this is going to be 6 sine of 3x cosine of 3x, and then we're done with that problem. Now, it even gets more interesting is when we start to put together different rules. Notice that this we have a product. I'm going to have to worry about the product rule, and then I'm going to have to worry about the chain rule. So it's a product rule with a chain rule inside. So when you're working through this, there are times where you kind of have to first apply the product rule, and then we'll do the chain rule in the second step. So remember, your product rule is you have 2 functions, function 1, function 2. So you're going to do x times the derivative of the secant of x squared plus x plus 1 with respect to x. You're going to do that first, plus your secant of x squared plus x plus 1 times your derivative of x, which is just 1. So I'm going to go ahead and do that because that one was easy. Notice that I kind of fill in my quote-unquote product rule, my f times g prime plus g times f prime, and any one that's hard, like that one with a chain rule in it, I'm going to do it on the next step. Right? Now that I have this filled in, now I'm getting ready to do the derivative of this. Bring your x down, so we have that. Bring your secant of x squared plus x plus 1. So I'm just bringing these 2 parts down. Now I need to figure out this derivative. So over here on this side, I'm going to think to myself, my u in that problem is x squared plus x plus 1. My du dx is 2x plus 1. So now I'm going to take the derivative of secant of u. The derivative of secant is secant tangent. So I'm going to do secant of u, x squared plus x plus 1, tangent of u, x squared plus x plus 1, and then don't forget you got to multiply that by your rate of change of your inside function, 2x plus 1. So as you can see, this can get fairly complicated fairly quickly. Now I am going to go ahead and I have a GCF, so I'm going to pull out the secant of x squared plus x plus 1. And then over here I'm going to be left with 2x plus 1, tangent x squared plus x plus 1, and that's all plus 1. And that was just to make it prettier, and I didn't feel like writing this twice. But does everybody see kind of the idea here? You have to be kind of very methodical. You have to first apply your product rule, and then within the product rule, you're going to have to apply the chain rule in order to do the derivative of the secant of x squared plus x plus 1. All right, let's do a couple more, and then we'll finish this video, do these last two. So the same thing here, notice that I'm getting chains within chains within chains. So you want to be very careful on this, and it might help, again, this is another one of those kind of rewrite it out. I'm taking the derivative with respect to m of my tangent 4 minus, and whenever I have powers on the trig functions, I like to pull them out like that and then cubed, because you got to figure out what's your inside function. All right, so I want to do the tangent, but it's a composition. I want to do this, but that's composition. You got to go all the way to the inside. Okay, so now I'm all the way to the inside. It's going to be the 5m. So u equals 5m. du dm is going to equal 5. Okay. So that's my u. And then I'm going to work myself out and go, well, the next thing is I have u cubed. I can do 4 minus u cubed together. Okay, that's another inside function. So I'm going to go v equals 4 minus u cubed. So dv du is going to be negative 3u squared. So I get that one in. So this is what I called v. And now I'm okay because I think I've got it out. Oh, you know what I forgot? There is an outside. I forgot to do the cosine. Let's come back. So you got to work yourself from outside in. You got to be careful. 5m is inside of cosine. So first I have cosine of u to do. So dv du. Derivative of cosine is negative sine u. There you go. So let me fix my little u. So u was only that part. This is now v. So let's do w for our next letter. W is going to be 4 minus w cubed. And there's my dw. W is going to be 4 minus v cubed. So dw dv is going to be negative 3v squared. Now we're getting there. So this was my w. And now I'm finally on the outside, so I can start putting myself together. What's the derivative of tangent of w? The derivative of tangent is secant squared of w. So we bring this all in, okay, times. So after I take the dy dw, now I got to go dw dv, negative 3v squared. Remember, v was cosine of 5m. Cosine of 5m. Okay. Times, so this is link 1. Here's link 2. Now I got to put my dv du in. So that's negative sine of u, which was 5m. Okay. And then our final link times du dm, which is going to be times 5. And so if we kind of look at each of these parts, this was dy dw, this was dw dv, this was dv du, and that last part is du dm, so I'm taking the derivative of this with respect to m, and everything cancels out. See, once you start getting chains within chains within chains, you've got to be very, very careful, and you have to recognize how many chains you're going to have. Every time you have, so this is 1, 2, 3, and then there's the fourth one. So there should be 4 links in your chain working your way from inside out. All right, let's take a look at this one. Now in this one, this very last one, kind of to finish out our lesson so far, is I'm going to treat this whole thing as the inside function. Because it doesn't really matter how complicated it is, as long as you can take the derivative of it. So I'm going to let u equal 3x minus 1 over x squared plus 3. When I calculate du dx, then I'm just using quotient rule. Low d high minus high d low all over low squared. It does not bother me how complicated that rate of change is. Now once I take that out, now I'm good. I only really had 2 functions. This really complicated inside function, and now this is u squared. The derivative of u squared is 2u to the 1 times the derivative of the inside function. So we end up with this whole nice complicated thing. We won't worry about simplifying right now. X squared plus 3 times 3 minus 3x minus 1 times 2x all over x squared plus 3, and I forgot to low d high minus high d low over low squared, so I'll fix that right now, and that would be your derivative. So the moral is that you always have to link the chains together. You have to have the derivative of the outside times the derivative of the inside. And if you have multiple inside functions, you go derivative of the outside times derivative of the next inside times derivative of the next inside until you put as many links in your chain as you have embedded functions. All right? So we'll stop this video at the end of example 1 and pick this up on the next one.